So here's a thinker question for you. You have this rectangular loop that's of wire that's carrying a current, is going round and round. So the top is going to the left, then for the side A is going straight down, then the bottom side B is going to the right, and for the side C on the right hand side, the current is going straight up. And the magnetic field as shown, all of the field lines, they're in the plane of this coil and they're going from left to right. So that's the direction of magnetic field. For the side C, for example, this is the direction of the current. So I want you to calculate the magnitudes of each of these forces. Remember, the force is given by IL cross B. So as far as the length is concerned, the height of the rectangle is being called H. The width of the rectangle, very reasonably, is being called W. So in terms of these symbols, and the magnetic field is big, great big capital B. So in terms of the symbols, find the value or the magnitude of the force first. That's the first thing to do. Second, find the direction of the forces. So for this top one, for example, the side D, the current is going to the left. Magnetic field is going over here. What happens to the wire? Is it getting pulled or pushed or lifted or lowered or whatever? Find the direction for the force on each of those sides of the rectangle, A, B, C, and D. And third, once you find the directions of all the forces, what's the overall consequence for that rectangle? So you have this rectangle loop of wire, the current is going around like that. What happens to that loop as a result of the combination of those four forces? So if possible, pause the video here and think about it, and we'll come back with the solution shortly. So this is what we have. First of all, on the sides D, the top one, and the bottom side B, there is no force. Why? Because the force equation is IL cross B. The magnitude of that, without the bar on top, that's the magnitude of the vector, is ILB sine theta. The theta is 0 degrees or 180 degrees. So here is the direction of the field, and there is the direction of the current. So here, this is 180 degrees. For the bottom one, that's the direction of the field, that's the direction of the current. So in this case, the angle is 0. In both cases, a sine of 0 and sine of 180 degrees is 0. So there's no force on the top and the bottom. As far as the sides are concerned, here is the current direction for side A, and then the field direction is like this. So when you do a QV cross B, you end up with a force which is pointing straight up from the paper. So the force is like this, is perpendicular to both of them. And that's shown with a circle with a dot coming towards you. On the other side here, for side C, this is the direction of the field. The current is going upward over here. Bring the tails of the vectors together, and then a QV cross B. So you start from, or IL cross B. So you go from IL to B. So you can't go this way because you have to go from IL to B, not from B to IL. So you have to go this way. It's pointing down, the thumb is pointing down. So the vector is going down into the plane of the paper, and that's shown in this manner. So what's the consequence of this? This side is getting pulled upward, and this side is getting pushed downward. So there's going to be a twisting action. You're lifting this and you're pushing that. So if you have some rectangle like this, okay, and then you lift this side and you push this side down, the effect is to try to rotate this rectangle. So this rectangle will feel a torque. So anytime you have a loop of current, a closed loop of current where the current is going round and round in whichever direction, if you put it flat in a magnetic field, there will be a torque on it. And depending on its alignment, you can have different torque. So next, let's find out how much that torque is. So before proceeding with the calculation, let me do a quick demonstration so you can see what's going on. So this was extracted from a YouTube short. So you have a coil that's hanging between the pole pieces of a magnet. So the magnetic field is in the plane of the torque, just like our thinker question. And you will see that when the current is turned on, once the current is going through the coil, there will be a torque, and the coil will turn to face the magnetic field. So let's play this thing now. You see, so that's basically what's going on. Here you have a coil with multiple loops. The current is going around, and that causes a torque on the thing, making it face the magnetic field. Now let's get back to the calculation that we were doing. So here's how the math works out. Here's the loop. You have side A, side B, side C, and side D. There's no force on the top and the bottom sides, D and B, as we saw. Here you have a force that's pointing upward. There you have a force that's going downward. Both result in a rotation the same direction. So if this is that coil, this is being lifted up, this is being pushed down. So you have a rotation viewed from the bottom. It looks like a counterclockwise direction for the torque and consequent possible rotation. So in any case, the torque is given by R cross F. R is the distance from the axis of rotation to where the force is applied. So if this thing is basically, here's my rectangle, that's my axis of rotation. So it's being rotated like this. This is my axis. So this distance is half the width of that rectangle. So if that's the width, the little w here, then the R from the axis of rotation is half of w. And F, as we saw before, is IL cross B. The B and the L, they're already crossed, so the angle is just 90 degrees. So the force is ILB. Now in this particular case, the L, the length of the wire, which is this thing over here, we call it H. It's the height of that rectangle. So you replace L with the symbol H, and then R is half of width, half of W, as we just discussed. And the angle between the R and the F is 90 degrees. So here is the direction of the force, for example. That's the direction of R. R is going this way. So in any case, the angle between the R and the force is 90 degrees. So that simplifies sine theta. Sine theta just becomes 1. So when you put all this together, the value of the torque just coming from the lifting force on side A, that's equal to half WIHB. And for the C, for this side here, the torque is the same. So even though that's the force that's pushing and this is lifting, it results in a torque in the same direction. So as a result, the rest of the math is the same. Tau C is the same. So the total torque on the loop is the sum of the torques caused by side A and side C. So take this and this, which are the same, and add them up. You get twice of one of them because they're equal. So the 2 and this half over here, they cancel each other out. You're left with WIHB. But note that when you multiply the width times the height, that's the area of the rectangle. Anytime you multiply the base times the height, the width times the height, that's the area of the rectangle. So we can replace the W times H with A. So now this ends up becoming, the 2's cancel. So this 2 cancels with this 2, and W times H is A. So you end up with the torque for the loop is IAB. Now this is when the loop is in plane, in the plane of the magnetic field. So you had this loop like this, and the magnetic field was in the plane. So this is what was resulting in a torque. Now, if you have an angle, the torque will try to rotate this so that this area over here, the area vector, is in the same direction as the magnetic field. The coil will rotate and try to align itself like this. So if it's at some angle, which is you'll have a 0 torque here. It's aligned. If it's like this, you have the torque that you just calculated. For intermediate situations, you have a correction factor, and that's the sine theta. So the torque on a loop in a magnetic field, if you put a loop in a magnetic field and there's some angle between them, it's not aligned or not completely facing the magnetic field, then the torque is equal to IAB sine theta. Theta is the angle between B and the area is normal. Now notice something interesting. Right now we calculate the torque on a loop of current, a wire that's carrying a current in a circular path. You put that in a magnetic field, and if the field is going this way, this wants to turn and align itself with the magnetic field. That's a lot like the electric dipole we saw earlier. If you have an electric dipole and this is an electric field going this way, this rotates and tries to align itself with the electric field. And we saw that from an earlier chapter, the torque on an electric dipole. So this is the dipole in the electric field. This is equal to Pe sine theta. So this expression here, the torque on a loop, IAB sine theta, it looks a lot like this. So if we combine I and A and call it a mu, which is the dipole moment for the magnetic case, just as P is the dipole moment for the electric case, then we get an equation that's very similar looking. So the torque now on a magnetic dipole, which is created with the loop, that's equal to mu B sine theta, where mu is IA. So it's just this previous equation that you had over here. And this mu now is a magnetic dipole moment. Just as P was the electric dipole moment, this mu is the magnetic dipole moment. And its unit is in amperes times meters squared. So in this second video on magnetism, we went from a wire carrying a current to a loop carrying a current in search of more excitement. Why stop with one loop when you can have many? So many practical applications, you don't just have one loop of wire, you have many turns of wire, n turns of wire, and that's going to amplify the effect. So here the mu that you have before, that is for a single turn. What happens when you have multiple turns, n turn? You basically amplify the effect. So for multiple turns, the torque ends up being, instead of just IAB sine theta, it's NIA sine theta. And that NIA, that's the magnetic dipole moment when you have multiple turns. And this can now be written as tau equals mu cross B in the same manner that you do for the electric dipole. The torque on an electric dipole is P cross E. This is the magnitude with a sine theta. This is the full vector expression. So you can have a direction for the torque coming from the cross product between the dipole moment vector and the B vector. And how that works, we'll see when we get to a solved example. Before we get into any number crunching, let me pause you with a thinker question. So we've seen so far that when you have a loop of wire with a current going around it, you put it in a magnetic field, it feels a torque. You have a magnetic dipole moment, but for that you have to pass electricity around in the form of a current. If you stop the current, this thing is gone. It's no more a magnet basically. How is it then that you have these things called permanent magnets? Where's the current? So look at this. Here's a little this thing. So see how this thing hops up? But the thing is, I'm not connecting it to a battery or anything. There is no current going around. How do these materials, some of which are actually insulated, how do they end up having magnetic properties with no supplied electric current? So just as a reminder, let's quickly look again at the demonstration of the loop carrying a current. Notice that only when the current is turned on does the thing become magnetic and is affected by a magnet. So here's a quick look at the demo again. So in the case of permanent magnets, where is the magnetism coming from? Why does it have a dipole moment? So think about this for a minute or so, and then I will get back to the answers shortly. So the short answer is something like this. There are circulating current, maybe not across the entire object in a macroscopic sense. However, they are made up of atoms. You have electrons going around an atom. That's a circulating current. So in the case of materials, even at an atomic level, you already have a magnetic dipole moment. And that current keeps going around forever. You don't have to supply it from a battery or anything like that. It's free and it's permanent. That's why this thing is called a permanent magnet. And not just the electrons circulating around the atoms in the form of orbitals, but each elementary particles like electrons and proton, they have something called a spin angular momentum. And these particles have a charge, and they do have a magnetic dipole moment even at the level of an individual electron. So in any case, materials already have magnetic moments in there. It's just a matter of them being organized in the right way for things to have magnetic properties. And one of the great things about a permanent magnet is you don't have to supply power. They're free. They're always there. So in electric cars, for example, often there's a combination of permanent magnets and electromagnets, the kind where you have to supply a current through a loop to produce the magnetism. So the permanent magnets are very economical, no power consumption. Now, in an earlier chapter, we talked about flipping an electric dipole. So if you have an electric field going in this direction, if I abruptly change the electric field to the other direction, this thing is going to rotate and flip over. Basically, it's going to point the other way. And there's an energy associated with flipping a dipole. That's what happens in a microwave oven. You have an electric field that's basically reversing its direction all the time. It causes the molecules to flip back and forth, and that energy gets conveyed to the food, and that's how the food heats up. So the same thing happens with a magnetic dipole moment. If you flip a dipole from one side to the other side, and energy is associated with the flipping. So in the electric case, the flip energy was 2pe, where p is the electric dipole moment and e is the electric field. So not surprisingly, to flip a magnetic dipole moment, it's a similar looking equation. You have 2 mu b. So the electric field is replaced by the magnetic field b, and the electric dipole moment P is replaced by the magnetic dipole moment mu. And here's this thing in action. So this is both of these have dipole moment. This is a compass and this is a permanent magnet. The compass has a permanent magnet shaped like a needle which can rotate. It's sitting on a fulcrum kind of. Now look at this. You see this is shooting out a magnetic field. This needle aligns with it. But if I flip the direction of this magnetic field, the needle flips also. So if I keep going back and forth like this, I can cause this to flip back and forth. And every time it does that, that's associated with a flip energy, which is 2 mu b. So this business of flipping a dipole back and forth and the energy associated with it is one of the important ingredients in MRI imaging, magnetic resonance imaging. So there you have a certain magnetic field. So to flip the dipole, you need this energy here, 2 mu b. When you shine this thing with RF radiation with a matching energy to this, you cause the thing to flip back and forth. You change the population of the moments which are facing one way versus the other. There are many other things that go into the MRI process, but this flip energy business is one of the important ingredients that goes into MRI. So here's a numerical example involving magnetic dipole moment. So we talked about the flip energy. We also talked about a torque. Every time you move the dipole away from the magnetic field direction, it basically wants to come back. So it requires work. It requires an effort, a torque to disalign this thing, to misalign it. So the question is, how much torque do you need so to rotate this thing to a certain angle that's out of alignment? So this is the zero angle when the dipole moment is along the magnetic field. There's a magnet, by the way. So the magnetic field lines are shooting out from the magnet and they're parallel to the dipole moment. That would be an angle of 0. So the question is, you have a bar magnet, that's the dipole moment there, the 8.55 10 to the 6 ampere meter squared. That's the standard unit for a dipole moment in MKSA system. What's the torque required to hold the magnet at an angle of 48 degrees from the direction of the applied magnetic field? And the field is 8.4 10 to the minus 2 Tesla. So it's aligned, and then you need a torque to rotate it away. How much torque do you need to hold it right here? Because if I let go of that torque, it snaps back. So that torque, it's equal to mu cross B. In this case, the torque is equal to mu b sine theta as far as the magnitude is concerned. This first thing over here, that's the vector equation. So the mu is the dipole moment, 8.55 10 to the 6. Just put that in there. B is the given magnetic field, that's the 8.4 10 to the minus 2. Then the sine theta, the angle of misalignment is 48 degrees. That's where the 48 goes, sine of 48. You crunch this baby out, and this is the torque. 5.34 10 to the 5 Newton meter. So that's, one heck of a torque to misalign the dipole. That's why the dipoles like to align very well with a magnetic field. Okay, so the last bit of business for this chapter on magnetism is the creation of a magnetic field. So far we've talked about the effect of a magnetic field. If you have a wire carrying a current, you put it in a magnetic field, it feels a force. If you have a loop carrying a current, you put it in a magnetic field, it feels a torque. But where did the magnetic field come from? So not surprisingly, the same thing. A loop of current can create a magnetic field. A wire carrying a current can create a magnetic field. So let's take this one step at a time. The simplest case is a wire carrying a current. So just as the force caused by a magnetic field has a strange right-hand thumb rule and cross product and all of that, so does the magnetic field created by a wire. Everything is surprising and kind of strange about the magnetism. So if you have a wire carrying a current, the magnetic field wraps around in the form of rings. So you have rings going around the wire that's carrying a current. And the direction of those rings is given by a different right-hand thumb rule. So here, so let me look at this picture over here. So this was kind of the best thing I could draw on a flat piece of paper. But if the current is going this way, the magnetic field is forming rings around it. And which way is the magnetic field pointing? Put your thumb along the direction of the current. The current is going to the left, and the fingers are curling in the direction of the magnetic field. So in this case over here, this is a nice three-dimensional model that I made. That's the current, the pencil, the blue pencil, and here's the magnetic field. It's going around. So it goes around in the form of rings. So while we're on the subject of magnetic field lines, let's see what they look like for some other common geometries. So for a dipole magnet like this, the magnetic field shoots out from the North Pole and enters from the South Pole. So it basically looks like this. So there's the bar magnet, and the magnetic field goes through it. It shoots out from the North Pole, and it gets sucked back in from the South Pole. The pattern actually looks a lot like the electric dipole. In the case of the electric dipole, you have a negative and positive charge. So the magnetic field shoots out from the positive and enters from the negative. One important difference, in the electric dipole, the field goes from the plus to minus even inside the dipole. Here, the field stays in the same direction. So it's not going from north to south within the magnet. It's going from north to south outside. But inside, it keeps going the same direction as the lines that you have outside. So these lines, they form complete loops, unbroken loops. That's not the case with the electric dipole. And if you have a coil, that's basically just like a dipole. So instead of a permanent magnet like this, if you have a single loop of wire with the current going around, or lots of loops in the form of a flat coil like this, then again, if the current is going around in this direction, the magnetic field shoots out from this side and re-enters from the other side. So this part, this side of this loop of wire or a flat coil looks like a North Pole, and the other side, it looks like a South Pole, to compare it with a permanent magnet. So the field pattern is very similar. So now let's get quantitative and find out what the magnetic field is numerically for a certain distance away from the wire. So now for the math. In the case of an electric charge, we found that the electric field, it drops off as 1 over r squared. It follows the inverse square law. Why? Because the electric field from a point charge goes in all directions. It spreads over the surface of a sphere. The area of a sphere is 4 pi r squared. So you have a dilution of 1 over r squared. It's getting spread over an area which is growing with r squared. So the strength of the electric field weakens as 1 over r squared. So you have the inverse square law. In the case of a wire carrying a current, like this thing over here, the magnetic field is not a sphere, it's a cylinder. The area of a cylinder goes as 2 pi r. So it's not r squared, it goes as 1 over r. So as a result, if for a cylindrical geometry, you have 1 over r, not a 1 over r squared. Because the area of a cylinder is 2 pi r L, it goes as r. So whereas for Coulomb's law, the electric field goes as kq over r squared, which can also be written as 1 over 4 pi epsilon 0, q over r squared, hence the 1 over r squared proportionality. In the case of a magnetic field, instead of Coulomb's law, you have something called an Ampere's law. and that gives you B in terms of the current rather than the charge, and you have 1 over R here, not R squared. And you have a constant here, just like you have the 1 over 4 pi epsilon 0. You have a constant here. It's mu 0 over 2 pi, where mu 0 is 1.26 10 to the minus 6 newtons per ampere squared. And this gives you the numerical value, the magnitude of the magnetic field. If you have a certain current passing through a wire at a certain distance, you have this magnetic field circulating, going around in rings. How strong is it? The farther away you get, the weaker it gets. It goes as 1 over R. And this expression gives you the actual value. That's the magnitude. As far as the direction is concerned, that comes from the right-hand thumb rule. So you already know it's wrapping around this thing like a cozy blanket. The question is, what's the direction of the magnetic field? Put your thumb along the direction in which the current is going. The fingers indicate how the magnetic field is circulating around that single wire. So that was the magnetic field going around a single very long wire. That is Ampere's law. As the name suggests, it's a law. This cannot be derived, it's a fact. In a way, it's related to single charges creating a magnetic field, another law called Biot-Savart law, but never mind. For our purposes, a wire carrying a current, a single long wire, has a magnetic field, is just an observed fact. That magnetic field is given by this expression here. It is a law. Now, however, you can look at the magnetic field for other geometries. Like, for example, a loop. If you have a single loop, where did my loop go? There it is. Okay, so for a single loop or a flat coil like this, you have a magnetic field. It's given by mu 0 I over 2R at the center of the loop or the short flat coil. Okay, so this is the magnetic field in the center of this. This acts like a magnet, as we've discussed before. That's the value of the magnetic field in terms of the current and the radius of this thing. Okay, and the mu 0 is the usual constant, the 1.26 10 to the minus 6. And if you have a long solenoid, if you have lots and lots of turns, rather than this flat pancake-like thing that I have, if this thing is long, you have many turns, like this over here, then the magnetic field is uniform inside the tunnel of that coil. Here's something that looks like a coil. So in the middle of this, the magnetic field is uniform, and that is given by mu 0 little n I. This little n is the number of turns per length. So assuming the turns are not stacked on top of each other, if each turn is individual and separate, then how many turns do you have per meter? That's what the little n is. And mu 0 is that same constant times the n times, of course, the more the current, the more the magnetic field. So this combination mu 0 ni, it gives you a magnetic field inside a long solenoid. So for some of the future exams you're likely to take, such as MCAT and so on, it seems you need to remember these formulas for the three main geometries: a long wire, a loop, and a long solenoid. So these are the three formulas. These two, by the way, they're not laws. You can derive this from the formula for a long wire, but these are formulas, and they would be, you may have to use them for certain types of problems. So talking about applying formulas to solve problems, here's an example of a problem. So you have a current going through this long straight wire like this. Next to that, you have a loop carrying a current. So those currents are different. These are independent circuits. So this thing over here is carrying a current of 5.4 ampere. And this loop is carrying a current of 6.3 ampere. So the current is just going around in this loop over here. It's a rectangular loop. And the question is, they gave you the currents and the long wire and the loop. They gave you the distances and the dimensions for this rectangle. What are the magnitude and the direction of the force acting on the loop if it has the dimensions given in the figure? So we are going to use Ampere's law. This thing is producing a magnetic field around it. Remember one of these things? When you have a wire, there's a magnetic field going around. So this wire is going like that. The current is going in this direction. You will have a magnetic field curling around. So on this side, on the right side of the wire, notice my fingers are basically going to poke into the paper. So here you have a magnetic field that's going in. Everywhere on this side of the wire, you have a magnetic field doing this. that the magnetic field makes circles. So it goes underground and comes up, and here the magnetic field will be pointing in the upward direction. But we don't care about that. Or where this other loop is, this thing circles and it's poking down into the paper. So these crosses, they represent the direction of the magnetic field in which this rectangular loop is lying. You want to find the force on the rectangular loop. Okay, so that's the direction of the B, the magnetic field. And then now one by one, calculate the current on each of these segments. So let's start with I'm calling this the upper segment. The upper segment is this thing over here, right next to that long wire. The lower segment, that's this long segment over here, far away from the wire. The ends we'll deal with later on. So let's proceed with that. So for the upper segment, first of all, this is the direction of B. Then this is the direction of the current, as you can see. Okay, so as a result, so here is B and here is the current. So as usual, you bring the tails together, bring the tails together like so. Then you go from the current to the magnetic field. It's IL cross B. It's not B cross IL. The order matters. So you go around like this, and notice my thumb is pointing this way. And that's why the force is in this direction, basically. So you have these two vectors, and then the final result of the cross product is perpendicular to both of these. So that's the force. So that's the direction of the force. Let's look at the lower segment, which is carrying 6.3 amperes as shown over here. Here the current is going in that direction. So there is the current. The magnetic field is still poking into the plane of the board. So here's your B, and there's your I. So as usual, bring the tails together. So lift this up until the tails are together like so. I'm sort of blocking the view. There they are. Okay, and then you curl your fingers from IL, the current direction. The current is going this way. So you curl your fingers from there to the direction of the B. And notice my thumb is pointing this way. So this is the direction of the force, in this direction. So the upper force is an attractive force. This top wire is getting pulled towards this long wire. And this lower wire here, it's a repulsive force. So this part of the wire over here, this one is getting pushed away. This one is getting pulled, because when two currents are in the same direction, just something to remember, anytime two currents are in the same direction, they attract. If they're in opposite directions, they repel. So we just proved that actually with the right hand thumb rule. And so we're going to find the force on this one, the force on this one, and you'll subtract this from the other one to find the net attractive force. So now for the numbers. So the net force is the sum of the upper plus the lower. The two ends, by the way, they cancel each other out because they're equidistant from that. The direction of the currents are opposite to each other. So the net force from these two will cancel each other out. So that leaves just the upper and this lower segment over here. Okay, so let's look at that now. So you're going to add these things vectorially. So the first one attracts. It's common to give an attractive force a negative sign, and then the repulsive force is a positive sign. If you wanted, you could break into the components. You could have an x-axis and a y-axis, and you'll come to the same conclusion. One is this is going to be negative because it's opposite to the x. This is positive. It's along the x. So in any case, now, so these are the signs. Now for the magnitude. So we saw earlier that the force on a wire that's carrying a current is IL cross B. The magnitude of that is ILB sine theta. And so this B is different for this wire and for this wire. The upper wire is closer to the long wire carrying a current, stronger magnetic field. This lower segment here is farther away. It's going to have a lower magnetic field. So the magnetic field will be different. So the I is the same. You have the 6.3 amperes going around the rectangle. So the I is the same for both our upper and lower segment. The length is the same, 40 centimeters for both of them. It's a rectangle. not a trapezoid or something like that. So the L is the same, but the B is different. So for the B, we need to use Ampere's law to find the magnetic field caused by a long straight wire, the thing at the very top. Okay, so let's go and combine these. So the sine theta is 90 degrees. We saw that the magnetic field is poking into the paper and the current is going like that. So they're at 90 degrees. So that takes care of the sine theta. It's simply 1. So where are we? So the sine theta is gone now. So you have ILB upper and ILB lower. So combine these and you end up with IL B lower minus B upper. So we have this thing over here. And so now let's go ahead and put some of the things that we know. The current is 6.3 amperes, and then the length of that wire is 40 centimeters. Convert to meters, so that's 0.4 meters. So the 6.3 times 0.4, that ends up giving you this 2.52. So let's call this equation 1. We need to find the magnetic fields to put them in here. So this shows the calculations of those two magnetic fields. The magnetic field is given by Ampere's law. You have a long straight wire. Magnetic field is in the form of ring. How strong? Mu 0 I over 2 pi r. So mu 0 is just a universal constant, 1.26 10 to the minus 6. The I is 5.4 amperes. So this is amperes. This was given. And then R, that's the distance from the long wire to where it is that you're looking at this circular field. So that's the radius. So that's the distance to the wire. So for that upper wire, which is closer, that distance is 2 centimeters away. It's shown on the figure. So convert to our standard units of meters. So that's 0.02 meters. So that's for the upper wire. And so you crunch this out and you get 5.414 10 to the minus 5 Tesla. That's the magnetic field going into the paper for that upper wire. Now for the lower wire, the lower part of the rectangle. So same equation, different numbers. So this part is the same, the current is the same, but that other lower segment is farther away, is the far side of the rectangle. So that's 12 centimeters away. Express that in meters, is 0.12, so this is now in meters. So you can crunch this out and you get about 9 times 10 to the minus 6 Tesla. So equations 2 and 3, they give you the magnetic fields produced by that first long wire at the two sides of the rectangle, upper side and the lower side. Now you can put this back into equation 1. So substitute the results of 2 and 3 back into equation 1. So equation 1 was this. So here's your equation 1. So you put those into that, and you end up with this thing over here. So actually, I'm hiding those other equations. There we go. So equation 2 and 3, equations 2 and 3, put them into equation 1. And so upon doing that, you end up with this expression over here. Crunch it out, and you get 1.137 10 to the minus 4 Newton. This is the total force on that rectangle. So that rectangle gets pulled towards that long wire. The negative sign, it indicates attractive. Okay, so this is what's happening basically. Going back to the original question. You have a current going this way and you have another current going this way. So this is getting pulled, this is getting pushed. But this force is weaker because it's farther away. So as a result, overall, the rectangle will get attracted towards that long wire carrying the 5.4. So if the rectangle is not fixed, it'll literally get pulled and it's going to go and touch that wire over there. So that's the final effect. And this is a good example where you have both the force caused by a magnetic field on that rectangle and the force created by a long wire carrying a current basically. So you have both the creation and the effect of the magnetic field wrapped into a single problem. Okay, so this serves as a good example for magnetic field caused forces.